Hello and welcome to our session, Building Scalable Inventory System with Azure Cosmos DB. Hi, my name is Sergiy Smyrnov. I'm Director Specialist, part of Cosmos DB Global Black Belt team.
Hey everyone, this is Marcelo Fonseca. I'm also part of the Azure Cosmos DB Global Black Belt team.
Today we're going to talk about real inventory availability system design approach using event sourcing, and we're going to showcase a couple of approaches with async and sync patterns to build those real-time inventories using Azure Cosmos DB. Let's first talk about the use case itself. In retail industry, ability to provide accurate inventory at scale with low latency is one of the core business requirements for all retail customers. Conceptually, this type of system need to process all the different inventory event types for node updates, catalog, inventory supply updates in a central system to calculate inventory availability for availability on hand, available to sell or on-hand quantities in real time, and supply read APIs to efficiently read the data for different presentation UI channels like cart checkout APIs, web search, third-party APIs, or demand forecasting. Let's look at one of the popular architectural design patterns which used to implement and solve the challenge to do it at scale in real time. So in that design approach, we usually ingest different immutable events for different inventory changes through ingestion service, apply some processing rules to, for example, reject order events if there is not enough availability on hand, and then write the qualified events into events ledger container. Then we have some kind of downstream processor in Cosmos DB. We're using change feed for that to process the data based on different event types, apply different rules, and then update snapshot states, which actually represent actual inventory, and build separate read APIs, which reads that inventory and supply it to all those online systems. It is inspired by one of the great examples we see online, right by Walmart for real-time inventory, and we actually see an implemented system in several POCs across large retailers in America. Now let's look how we implemented the design pattern with Cosmos DB. In our case, we use inventory event feed to inject different inventory types discriminated by type into the Azure function create async inventory event, which also used as a business rule validation for one of those examples I mentioned, and then write qualified events into inventory ledger container. Then we have change feed Azure function trigger, which listen for all the mutation in that ledger container, take all the documents, interrogate event type, and then based on different event types, use patch API in Cosmos DB to patch state of the inventory in different container called inventory snapshot. And then we have the simple read API function, which using the read by key, partition key, and ID to do a point lookups of those inventory documents. In addition to this, we can potentially build analytics or HTAP reporting solution using Fabric Mirroring. This is out of scope for today, but this is also a very viable solution. This repo exists in repo link aka.ms cosmos db-inventory. You can also try it yourself. Now, let's look at quickly at the demo of that inventory, how we executed and implemented it. I'm going to jump quickly to an example. So first, let's see what's deployed. We have Cosmos DB deployed, a couple of the functions for APIs and also for the change feed worker. From the Cosmos DB, we have two containers, inventory ledger container, which has inventory items. They are partitioned by the partition key, which synthetically produce node and the SKU number. And then we have the unique GUIDs for ID to define the uniqueness and immutability of the events. And then we have inventory snapshot container, which has a snapshot view of on-hand active customer reservations available to sell, etc. And then a couple of timestamps to carry over and use for conditional processing. Now let's see how that works in the reality. So we define the partition key as one of those keys, and then we can use simple REST APIs to test this work. Let's first check what the current inventory is showing. So when we run the get async snapshot, we have on hand about 13,000, and then available to sell 12. 1950. Now, as we send requests for create async inventory to update the inventories with the quantity of 1000, this inventory will, so this is our new inventory process. Now, if we run this get async snapshot again, we can actually see that, yes, we can actually see that our on hand and available to sell increased. Now, as we submit different type of inventories, changes, so like let's reserve 15 attributes of this, we can actually see that now the quantities will change as well. So now we have available to sell lower, while we have on hand still higher. So as we now change the order shipped, we can actually see that our on hand also will change now because we actually sent. Now let's look at the reverse. Like if let's say we cancel order and we'll get 10 back. So as we process this, we can also see that available to sell now change back again, and same thing when we actually return order, our on hand also will change. It increased back. So this kind of shows the flow of the document events between the ledger container and snapshot container and how we can read it. Let's look at the code and how it's implemented. So from the code, we have a couple of functions, and then for APIs, and then the worker process. For get async snapshot, we're using a simple partition key ID, read by ID API. For create async inventory, we using a couple of validation rules. At the end of the day, we do in simple write create document, but on the validation, we actually use reserved we use low availability threshold parameterized value, and then evaluate reservations by first reading inventory snapshot to check if we have enough inventory, and then process available to sell less than reserved quantity. And then furthermore, we actually can check if reserved quantity is not enough. We also check if we have anything in flight for the same partition key, because potentially there could be events in the downstream which has not been processed yet, and that would guarantee that we can minimize a possibility of overselling for any hot item. And then the last piece is on inventory processor. It's using the Cosmos DB change trigger, which is implementing downstream processing based on the different inventory items, inventory types. We use Cosmos DB patch operation, and then in the patch operation, you can see that we increment on hand based on the on hand quantity, and then increment available to sell, and then updating the event timestamp and last updated timestamp. Event timestamp is _TS, which is internal timestamp we carry over from the document itself, from the event document. This is actually very important because we use conditional patch API feature called conditional patch option, where we validating that we only patch document if the inventory event timestamp, if last event timestamp less than inventory event. This is done to ensure that we do not update the inventory twice for events which are reprocessed, because change feed does not guarantee only once delivery. It guarantees at least once delivery. So if the function is restarted or there is some kind of reprocessing, we can skip the documents events which already been processed once. And then as we implement different inventory snapshots, we also can raise an alert or put it in an error queue or some kind of alert. And I actually simulated a couple of those where my inventory processor sent the error that inventory snapshot was not updated because was not enough reservations or duplicate processing. And this is just basically a message you can catch an exception and then process downstream. So this is basically the simple example how this works. Now, if we go further, and you can say that, well, this is all great, but how can we prove that this is architecture scalable? For that, we simulated about 10,000 transactions per second, where we split in about 80-20, 20% for writes and 80% for reads. And we were able to simulate 2,500 writes per second and over 8,000 reads per second for 60-minute duration of the test. And you can see the graphs for reads, writes, and then the small graph is for change feed reads. And you can see at the bottom that the percentage duration for those latencies at scale running at high concurrency was only 2.3 milliseconds for read operations against snapshot and 4 milliseconds for absurds in the ledger container. And this is further proven that Cosmos DB is very scalable database with low latency, and this is actually within our SLA's guarantees that point reads and writes are less than 10 milliseconds at P99. Now, the cherry on top, running this high throughput workload does not have to cost arm and leg. Combined across 3 containers, this whole workload costs about $3,600 a month, projected based on the list price, plus maybe a few $100 for storage based on 25 cents per gig. And you can see that we actually, from our RU perspective, those containers fairly small. It's 16,000 are used for ledger, 40,000 for snapshot, and 5,000 for leases. And you can see that the 2 screenshots at the bottom showing the per partition normalized RU percentage usage, and more importantly, the RU distribution across multiple partitions. As we scaling out our ledger and snapshot containers, we allow to scale out our work in a fairly distributed manner to show that we can continue to scale out and achieve that near linear scalability for the workload if we need to scale more. I want to point out a couple of tuning gotchas we implemented here to achieve that scalability. For inventory ledger container, we scale it out to 10 physical partitions, even though we have 16,000 RUs. To do so, we have to scale up Cosmos DB to 100,000 RUs and then scale down. The reason for that is this is done to allow downstream change feed processor, that inventory processing worker, to scale out its compute as well in order to not to bottleneck the downstream processing. This is actually a very common trick we use when we have to scale up the change feed, because Azure Functions will automatically start function instance for every physical partition in Cosmos DB and process it in parallel. So if we need to process downstream fast, all we need to do is scale out 4 scale out partitions to process downstream, and then also scale out some inventory snapshots to be able to patch it efficiently while we're doing the reads. With that, I'm going to transition to Marcelo, who can explain more on how to do it with sync pattern.
Thank you, Sergiy. So as we saw, the sync pattern allows us to scale writes and reads independently. But what if your business doesn't allow any kind of overbooking and needs to guarantee 100% availability to sell quantity even during large order events or reservation spikes? So in a sync pattern, there is a small chance of overbookings, and even if with some guardrails that we actually implemented, or in our case, for example, back pressure during replication, where it makes experience some lag, it may happen. So the sync pattern solves this issue and gives you the guarantee, because Cosmos DB supports ACID transactions within the same partition key scope via transactional batch. And the trade-off for this ACID sync pattern is write events and reads must share the same partition key and must reside within the same container, so they cannot scale independently. The overall architecture, as we can see here, is quite similar. So we do have the same inventory feed here, but our create sync inventory event API is responsible for both scenarios, the business rules and also persisting data to Cosmos DB. So we have, in this case, a single collection, and the read API is pretty much the same. So the trick here is that the inventory event function is using transactional batch feature to increment and decrement product availability at the same time, and again with ACID guarantees. So let's check the code in action. So here we have our create sync inventory event function, which is an HTTP function. And here we have some business rules to route the proper method for handling each event. And for example, let's scroll down here to order item reserved, right? So this item reserve method needs to check the availability. So in this case, we are also using the same patch API. We are decrementing, for example, availability to sell, adding, incrementing active customer reservations, patching the date, and again, using our conditional, our filter predicate or conditional patch operation to check whether the available to sell minus the reserved quantity is greater or equal than 0 to avoid any kind of overselling. Just to make sure we are on the same page, we for this transactional batch to happen, we must be within the same partition key. And we are also using our transactional batch to guarantee the ACID behavior. So at the same time, we are executing a patch API to the snapshot object, as well as create the inventory event for record. Just to remind that in this particular case, in case of a conflict or a preconditional failure, in this case, if we are kind of overselling, the caller is responsible for retrying the call. So let's jump to the portal. As you can see, we have a single collection, a sync inventory collection. We have several items sharing the same partition key. So each one of those items here with a guild as an ID are different events. We are also sharing and storing different event types within the same collection, as well as we are storing the snapshot in the same container. So let's see it running. So in this particular case, we are calling the get snapshot API. We are seeing that we have available to sell 10,000 items. We are updating the inventory with an extra 10,000. If we check it again, we have now 11,000 records. Now let's quickly reserve an item. So we reserved 1,000 items. As you can see, we now moved 1,000 items to the active customer reservation. We still have 11,000 on hand and 10,000 available to sell. If we now ship the order, and one thing it's interesting to see, I'm kind of shipping a value greater than we actually reserved. So business rules actually apply here. We don't have enough reserved quantity to ship. Now let's ship 1,000 documents. Now we ship 1,000 items, and now we just have 10,000 on hand and no active customer reservations. To quickly show one interesting feature here that we added in the portal, we now have a CoPilot for queries in Cosmos. So let's try it out. So let's, for our partition key, specific product, count events newer than this particular date, and aggregate by event type and exclude our snapshots. So once we hit, it generates the query for us. All we have to do is execute. There we go. And we have our aggregation here in place. So let's move back to our presentation. So same thing here. We ran this execution for about an hour. We sustained about 1,900 writes per second with a P99 of 8.5 milliseconds. We also sustained about 7,600 point reads per second with a P99 of 2.1 milliseconds. So the workload itself is sustained. The curve is pretty much flat here, and with even though we have a high consumption here, we still have a low response time. So finally here, this container has only 50,000 RUs in 5 different physical partitions. That will cost about $3,000 per month, estimated with a full month. And as you can see, we have a flat consumption and evenly distributed workload among all those physical partitions. And to wrap up here, if you want to try it yourself, again, the repo is available in GitHub, and you can just clone and test it yourself. And if you haven't tried Cosmos yet, you can try it for free. We have available documentation with tutorials, best practices, and if you want to learn more about Cosmos DB, we also have a learning path available for you. With that, thank you very much. Enjoy the rest of the event.